Welcome to our lesson on electrochemical cells. Today we'll explore three important types: the dry cell, the lead-acid storage battery, and the hydrogen fuel cell. Each of these cells converts chemical energy into electrical energy, but they do so in different ways and have different applications. Let's start with the dry cell, also known as the Leclanche cell or zinc-carbon battery. This primary cell has a zinc container that serves as the anode, a carbon rod in the center that serves as the cathode, and an electrolyte paste of ammonium chloride. The cathode is surrounded by a mixture of manganese dioxide and carbon. During discharge, zinc atoms at the anode lose electrons, forming zinc ions. At the cathode, manganese dioxide accepts these electrons in a complex reaction, producing manganese oxide, ammonia, and water. A typical dry cell produces about 1.5 volts. It's inexpensive and readily available, making it popular for everyday devices like flashlights and toys. However, it cannot be recharged and has a limited lifespan. The voltage also drops under heavy loads as the chemicals are depleted. Now, let's examine the lead-acid storage battery, which is a secondary or rechargeable cell. This battery consists of lead plates as the anode, lead dioxide plates as the cathode, and sulfuric acid as the electrolyte. During discharge, both the lead anode and the lead dioxide cathode react with sulfuric acid to form lead sulfate. At the anode, lead is oxidized to lead sulfate, releasing electrons. At the cathode, lead dioxide is reduced to lead sulfate, consuming electrons. The overall reaction results in the conversion of lead and lead dioxide to lead sulfate, with a decrease in sulfuric acid concentration. Each lead-acid cell produces about 2 volts. A typical car battery has 6 cells connected in series, giving 12 volts total. The main advantage of lead-acid batteries is that they can be recharged hundreds of times and can provide high surge currents, which is perfect for starting car engines. However, they are heavy, have relatively low energy density, and require maintenance to keep the electrolyte at the proper level. Finally, let's examine the hydrogen fuel cell, which continuously converts chemical energy to electricity as long as fuel is supplied. A typical proton exchange membrane fuel cell consists of an anode catalyst where hydrogen is oxidized, a cathode catalyst where oxygen is reduced, and a proton exchange membrane as the electrolyte. At the anode, hydrogen molecules split into protons and electrons. The protons pass through the membrane, while the electrons travel through an external circuit, generating electricity. At the cathode, oxygen combines with the protons and electrons to form water, which is the only byproduct. An ideal hydrogen fuel cell has a theoretical voltage of 1.23 volts, though practical cells typically operate at 0.6 to 0.8 volts under load. Fuel cells have several advantages. They can operate continuously as long as fuel is supplied. They have high efficiency, and when using hydrogen, the only byproduct is water, making them environmentally friendly. However, they require pure hydrogen, use expensive catalysts like platinum, and face infrastructure challenges for hydrogen storage and distribution. Let's summarize and compare these three electrochemical cells. The dry cell is a primary, non-rechargeable cell that produces about 1.5 volts. It's inexpensive but has limited life. The lead-acid battery is a secondary, rechargeable cell that produces about 2 volts per cell. It's heavier but can deliver high current. The hydrogen fuel cell continuously converts fuel to electricity with high efficiency and low emissions, but requires hydrogen infrastructure. Understanding these different types of electrochemical cells helps us choose the right technology for specific applications.